The title of this part of the lecture is Rutherford formula. Rutherford formula was derived in order to interpret results of experiment which consisted in scattering of alpha particles from a foil of gold. Alpha particles are double ionized helium atoms. They can be obtained from radioactive sources, and such radiative sources existed at that time. This scattering experiment was made in the time, by the way, it was about a century ago, when the knowledge of atom structure was very scarce. And it was known that electrons are contained inside atom because they could be observed in emission from atoms. And on the other hand, it was known that atom as a whole was neutral. As it was neutral and electrons were known to be light particles with mass which could not explain all the mass of atom, so most of the mass of atom was assigned to a matter or positively charged matter, and in the model developed by Thomson, model which was sometimes called as a pudding with raisins because it resembles it, positive charge was uniformly distributed in the whole volume of the atom, and it contained most of the mass of atom, and electrons were located somewhere inside, and number of electrons was such as to compensate positive charge of atom. Then, as a whole, atom was neutral, as was actually observed in experiments. In case such an atom is contained in a foil, expected scattering is scattering on small angles only, because from the laws of classical mechanics we know that when heavier particle is collides with lighter particle, it cannot be scattered in backward direction. So when alpha particle, which is much heavier than electron, after penetration into this atom collides with electron, it can scatter only in the forward direction, not in the backward direction. And when this particle penetrates until it penetrates the atom, as far as atom is neutral, so and it has some plus charge, but nevertheless there is no interaction because atom is neutral. But when it penetrates the atom, it appears inside atom, inside field of positive charge, not uniform because there are somewhere electrons, and in this case it is possible that some small deviation of trajectory of this particle of a particle may occur, but it is absolutely forbidden for this particle to be scattered in backward direction. Surprisingly, in the result of this experiment, such particles which were scattered in backward direction were observed, and this made Rutherford to produce a new model which differed from model of Thomson in a sense that positive charge was concentrated in some small volume, and most of the mass was also concentrated in small volume. When we say small, we mean small volume as compared with whole volume of the atom, and the rest of the volume is filled somehow distributed electrons. And then, as this positive charge is concentrated, alpha particle, which moves in this direction, experience Coulomb force, and because it is also charged with plus, and it can, as this nucleus is heavy, it can be scattered in backward direction. If it is head-on collision, so this returns back to the point of origin, and if it goes somewhere here, it is just due to this repulsion, it changes its trajectory and is scattered at some small angle. But sometimes it can be scattered in backward direction. Now we will look at the force, and force between alpha particle and the nucleus is Coulomb force, and Coulomb force, we know that Coulomb force F is K Q1 Q2 over R squared, when K is coefficient which depends on the system of units, and in C system is 1 over 4 pi epsilon 0. This in atomic physics we will use system in which K is equal to 1, and if we consider a scheme of this experiment, here we have a nucleus, this we call now nucleus, and this nucleus has positive charge Z E, where Z is atomic number of target nuclei. If this is axis along which alpha particles are impinged on the foil, then if this is alpha particle or other particle, in this case alpha, it has a charge plus Z small e. For helium, Z is equal to, and this is trajectory of this particle. When it is closer to the nucleus, it starts deviate from its initial direction, and this is trajectory of such particle. This distance between axes through the center of nucleus and direction of trajectory, we will denote it with B, and it is called impact parameter. Taking into account these charges, we can rewrite this force as F is Z is squared over R squared, and we understand that when particle propagates in this direction, so F is changing all the time because R is changing, and we will now look at moments. Initial moment of this projectile is P0, and after interaction here moment is P, and we can denote the angle of scattering as theta. And now let's draw a moment diagram of moments, taking into account that in the system with no external forces, and due to fact that so we have law of conservation of energy, then P0 absolute value should be equal to P absolute value. That means that momentum changes only direction, not absolute value, so internal energy between these two particles remains unchanged. Now in diagram, this we will denote P0, and P1 is at this angle, and the length of this vector is the same as this vector because of this equality. And then this vector will be delta P. So delta P is here. This is a scattering angle, theta. Now these sides of this triangle are equal. Then this is theta over 2. And this angle is pi minus theta over 2, because pi is sum of three angles of triangle. From this diagram we can derive delta P to be equal to 2 pi 0 sine theta over 2, or this is 2 mv sine theta over 2, where m is a mass of projectile and v is velocity of projectile on infinity when it is far from this. So it is initial P0 is initial momentum. Now we can consider the same scattering, taking into account laws of classical mechanics, and from the second Newton's law we have that delta P can be found as an integral of f dt, or in projection on this direction of delta P, we have absolute value of delta P is integral of Fn dt, where Fn is a projection of F on direction delta P. In this problem we will characterize the position of projectile relative to the center of scattering, which coincides with center of nucleus, in polar system. In this system here is distance r for current position of projectile, and this angle is phi. And during the scattering we assume that this nucleus is so heavy that it remains in stationary position, and is not shifted in the process of scattering when it is very heavy. Only relatively light particle is changing its trajectory. Then to find this Fn, we need the angle of projection, and this angle is here. It is angle psi. Then Fn is f cosine psi. This angle is pi minus theta over 2. Then psi is pi over 2 minus theta over 2 minus phi. So Fn is f cosine pi over 2 minus theta over 2 minus phi, and is equal to f sine phi plus theta over 2. If we substitute this force here, we will obtain z is squared over r squared sine phi plus theta over 2. Now we can substitute this Fn into integral, and we will obtain that delta p is z is squared integral of sine phi plus theta over 2 over r squared dt. Unfortunately, we have here different variables under integral sign, because when t changes, particle moves along trajectory, and r changes and phi changes. To resolve this problem, first we will substitute phi dot, we will denote it as d phi over dt, from which we can write that the t is d phi over phi dot, and then this is z is squared integral sine phi plus theta over 2, and here we have r squared phi dot dt, d phi. Now we have to remember from classical mechanics a law of conservation of angular momentum, and angular momentum for point mass is m r squared phi dot, where phi dot is angular velocity, and this momentum is relative to this center of scattering, and when a particle is far away here, its momentum is just m v. This is momentum, and angular momentum is mv and b. So this trajectory is shifted by b from this axis. And as far as conservation of momentum is provided, because this force which acts between particles is central force, which goes through the center, the action of this force is those centers of the particles, then this momentum, angular momentum, is all the time the same, so we can equate this. And from this we can substitute VB instead of r squared phi dot. This results in z e squared divided by VB, and V and B in the process of scattering are constant for a given particle. And here is integral sine phi plus theta over 2 d phi. Now let's look what are the limits of integration. So in the initial moment when this particle is far away in the left part of the figure, the phi is 0. And when it goes in that way and is far away from the center of scattering, this angle is pi minus theta. The angle, I mean angle of phi. So phi is from 0 to pi minus theta. Next, we need to find this integral. Let's do this. So we need to take integral, which is integral from 0 to pi minus theta of sine phi plus theta over 2 d phi. Well, I will substitute new variable which is high, and this high is phi plus theta over 2. Then d phi is d high, and when phi is 0, high is theta over 2, and when phi is pi minus theta, high is pi minus theta over 2. After this substitution, I have that this integral is integral from theta over 2 to pi minus theta over 2 sine phi d phi, and this is minus cosine phi, and limits from theta over 2 to pi minus theta over 2, and this is 2 cosine theta over 2. Therefore, we have, if we look now back to this formula, we have now delta P is equal to z e squared over VB 2 cosine delta over 2. Now we can compare the obtained result with this result, which we obtained from consideration of vector diagram of momenta, and to equate this and that. This results in 2 mv sine theta over 2 is equal to z e squared over vb 2 cosine theta over 2. From this we can derive that mv squared over z e squared b is cotangent theta over 2. This is the relation between impact parameter and scattering angle. It is important for us because experimentally we can measure angles of scattering by location some detector system here at different angles, but there is no way to find impact parameter for each of collisions because different atoms pass this different projectiles pass target atoms at different distances, and we can only measure average number of particles which are registered at different angles. We cannot go into the foil and measure this B for each particle which passes through the foil. So it is very important to find this relation between impact parameter and theta. And impact parameter is necessary for us because physics is here in impact parameter. Depending on impact parameter, we have different scattering, and we have different possibility or probability to find a particle scattered at a given angle. In order to explain this, I will try to draw some picture and imagine that this is the target nucleus, and we will draw here two circles around it. And let the radius of inner circle is b, impact parameter. So if a particle goes at this distance, then it is deflected at some angle theta. And if it goes here, it is farther than this, so it will be deflected at smaller angle. And of course the same here. Then this is axis through the scattering center. This is B, and this is dB. Now, if a particle is scattered at angle theta, this is angle theta, and this is d theta. So, if particles are scattered in the interval from theta to theta plus d theta, then the impact parameter changes from b to b plus dB. Then if particles go here through this ring, which is hatched here, then they will deflected or scattered on angles in this interval. Now we can, when we understand this, we can look at the foil, and when we look at the foil, and project this figure here, we have some atom here, and here are these circles, and this is this hatched area, and we assume that this is thickness of foil equal to d, and the whole area of this foil is S. Then a ratio of this area around this single atom to total area of this foil give us a probability for particle to be scattered on this angle, because when it goes here, and if its trajectory goes through this hatched area, then it is scattered on angles in this interval. But ratio of this hatched area, if it goes somewhere else, it will deflect it at different angle. So this ratio gives us probability to find a particle deflected of this angle. But we have to take into account that there is not only a single atom, there is a lot of atoms, and such rings are surrounds all these atoms. So if there are many atoms, we have to multiply this area of this ring by number of atoms in the foil. If we denote by n small the density of atoms in the foil, so then n has a dimension of atoms in meter cube, then total number of these atoms is n, and the volume of this foil. If we denote dn theta, number of particles which are reflected in this interval, then the ratio of dn theta to n is equal to ratio of the area of all these rings to area of all foil. Area of all these rings is n multiplied by volume of the foil is S d, and one ring has this ring has area 2p by db, where db is the width of this ring, then multiplied by 2 pi b db. And here is total S, so this ratio is equal to this ratio. Now we have substitute here b and db. B we can derive from this b, and db also from this by taking a derivative from left and right sides. So we have that mv squared over z is squared db is equal to minus 1 over sine squared theta over 2 1/2 d theta. Now we can substitute this b and b from this, and db from this, and in this case in right part of equation we will have a look ratio of cotangent theta over 2 divided by sine squared theta over 2. Let's evaluate what is this. This cotangent of theta over 2 divided by sine squared theta over 2 is cotangent is cosine theta over 2 divided by sine theta over 2. Here is sine squared theta over 2 Now I will multiply numerator and denominator by sine theta over 2. Here sine theta over 2. And this is equal, here is, this is 1/2 of sine theta. So this is sine theta divided by 2 sine in fourth power theta over 2. Now we can rewrite this, and if we substitute what was found, we will obtain the following result, that this is nd z e squared divided by m v squared, and all this squared, and here 2 pi sine theta d theta divided by 4 sine in fourth power theta over 2. But this 2 pi sine theta d theta, this is d omega, solid angle, which in this case we have, okay, if we draw it here, so we have 2 rings. This should be, of course, somehow in this direction. So we have this cone in which these particles goes in this interval of angles, which is actually this d omega, and the final formula is dn theta on n is nd z e squared over m v squared squared d omega on 4 sine in fourth theta over 2. This is Rutherford formula. Since we assumed that the target nucleus was in the same position all the time, this formula is correct only if we consider it in center of mass in laboratory system. Actually, this slight shift will result in some changes in this formula, but from theoretical point of view it is correct, and the main interest is to what extent this formula can predict results of the experiment which was made in Rutherford laboratory. And it appears that this formula very closely reproduced the results of measurements. That means that the idea of scattering of projectiles on nucleus was productive. This means that the Thomson model was wrong, and a new model should be developed. And this model should take into account that nucleus is a center of atom in which concentrated most of mass of the atom, and this nucleus occupy only a small part of the atom as a whole. And this result was a breakthrough in understanding of atomic physics, and it contradicted significantly the current knowledge which existed at that time. The problem is that such a system could not exist in, from the point of view of classical physics, because if we consider such a system, in the center of atom we put a positive nucleus and some electrons around this nucleus, then the question arises how these electrons behave in the atom. If, for example, if they are moving all the time, they can move only in closed finite volume, so they should move with acceleration. In case they move along some closed trajectory, then centripetal acceleration will result in emission of radiation from atom, since we know that if charged particle moves with acceleration, it emits electromagnetic waves. Electromagnetic waves take away some energy from atom, and very soon atom would collapse in such a model. If we try to fix the electrons in some locations without movement, this construction, the structure of atom would contradict Earnshaw theorem, which we studied in electrostatics. And Earnshaw theorem stated that for point-like charged particles, the configuration when this is stationary, for stationary configuration, stable equilibrium cannot be reached. So this atom would be not stable because of Earnshaw theorem. Then this demonstrates us that something is wrong when we try to apply known knowledge to this micro-object which is atom. Some new concepts and new ideas were needed in order to overcome this problem, and we will see in following lectures how this was done.